Hello, my name is Tawanda Zimudzi, and I'm going to talk to you a little bit about using FTIR, specifically attenuated total reflection, to do depth profiling in materials. And just to start off with, I'm just going to give you a little bit of an introduction to molecular spectroscopy. So in molecular spectroscopy, we use light of various wavelengths, and we see how that light interacts with matter. So basically, have light, we place a sample between the light and a detector. In the case of infrared spectroscopy, this could be either be a mercury cadmium telluride detector or a deuterated triglycerin sulfate detector. And then we look at how that light interacts with our sample, whether it's transmitted, whether it's scattered, or whether it's reflected. And we get all sorts of information from that reflected or transmitted light that comes out of our sample. And there's several ways that we can place our sample in the path of the infrared light. The simplest, most straightforward way of doing this is sampling geometry known as transmission. And with transmission, we basically have our sample sitting in the path of the light, and the light just goes through the sample. And the sample could either be a thin film, it could be a powder sample that is mixed with potassium bromide and pressed into a pellet. And as long as that sample is IR transparent to some degree, some light will get to the detector and will get information about your sample that way. Another way that we can measure your sample is by doing external reflection. And there are two very closely related geometries for external reflection. There's specular reflection, where the light just hits your sample surface. Some of that light is absorbed and some of it is reflected. We measure the reflected light and can glean a little bit about what was absorbed by looking at the difference between the reflection of our sample and the reflection of a standard. And in most cases, we use something like gold. Closely related to that is reflection absorption, which is very similar geometry, except in this case, the sample is sitting on top of a reflective substrate, which could be gold or anything that's metallic and reflective is usually the ones that are used. And with reflection, we can actually look at things like orientation of samples. We can look at thickness measurements by looking at interference patterns through the sample. And so there's lots of information that we can get from these external reflection geometries as well. We can also look at samples using something that's known as attenuated total reflection, and I'll go into more detail about that in the next slide. And with attenuated total reflection, we basically have a high refractive index crystal where the light goes through and a little bit of light propagates through a sample when it's in contact with that high refractive index crystal, and we get IR absorption that way. And it's used for routine chemical analysis because there's very little sample prep that's required for attenuated total reflection, or ATR. And it can give us information about orientation, and I'm going to talk a little bit more today about how we can do depth profiling. Another way that we can measure your sample, which I'm not going to go into in this slide in much detail, is diffuse reflection. And it's very similar to specular reflection, except that we get a specular component of light that's reflected off your sample, and then we get lots of diffusely reflected light that comes off. And we're specifically measuring that diffusely reflected component of the light. And it's used a lot for trace contaminants. It's used a lot for in situ measurements. So if you're doing anything in the realm of catalysis, for example, diffuse reflection is going to be the one that's going to be used the most. Gas absorption, if you're looking at rough surfaces, or if you're looking at powders, because it gives such good sensitivity. But digging back into attenuated total reflection, the reason that sampling geometries are important is because they influence what the spectrum is ultimately going to look like. So in this example that you're looking at here, we've got different spectra of hydroxyapatite. And you'll notice that each of those spectra actually look different despite the fact that we're looking at the same sample. So for example, if you look at the drifts spectrum of hydroxyapatite, you'll see a pretty distinct sharp peak at about 3,000 wave numbers because of the OH vibration in that material. And you'll notice that if you look at a diluted drift spectrum, which is the one in red, that peak becomes a little bit smaller, and we start to see features closer to about 500 wave numbers that we don't see in the blue spectrum. And that's because of the difference in the artifacts that we see between diluted and not diluted drift spectra. And then if we take that exact same sample and then look at it with diamond ATR, you'll notice that that peak that was very obvious and apparent in drifts is no longer easy to see with the diamond ATR. And you'll notice that you've got peak ratios at around 1,000 wave numbers, where you see a few peaks there, what looks like a little bit of like sharp peaks on the right-hand side of that main peak that are pretty apparent with diamond ATR. But if we move to germanium ATR, you'll notice that the ratio of those peaks has changed. And that's because of something that I'll mention in a few slides, which is the variation of penetration depth with wave number. And you'll also notice that the peak that we could see at around 500 wave numbers, no longer easy to see. And that's because the germanium material does not actually transmit light below around 650 wave numbers. So with that in mind, I will move on and talk a little bit about how attenuated total reflection works and how we can use that to profile samples. In attenuated total reflection, we have a high refractive index crystal material, which could either be diamond, could be zinc selenide, could be germanium, it could be silicon. And we place our sample on top of that high refractive index material, and then we shine light through that high refractive index material at an angle that's above the critical angle. And under those conditions, what happens is that the light, instead of refracting out of our crystal, is reflected back towards the detector, and we call that a total internal reflection. While that's happening, there's a little bit of electromagnetic radiation that's propagating at the surface of our crystal, which we call the evanescent wave. So if we put a sample on top of the evanescent of the crystal, and that sample absorbs infrared radiation, we will get a reduction or an attenuation of that reflected beam, and that attenuation will occur at frequencies that correspond to where our sample absorbs IR light. And that's the principle of attenuated total reflection, and that's how we get information about our sample using it. And the interesting thing about attenuated total reflection, which makes it really useful for depth profiling, is that the evanescent wave does not propagate all the way through your sample. It propagates a finite amount into your sample, and that amount that it propagates into your sample is a function of a few things. It's a function of the incident angle, it's a function of the refractive index of the sample, and the function of the refractive index of the crystal material. And I'll go into depth about that in the next slide. So the depth of penetration that you get in attenuated total reflection depends on several factors. It depends on the refractive index of the sample, which we often don't have any choice in. It depends on the refractive index of the ATR crystal, which we can sometimes vary. And it depends on the angle of incidence that we use for the light. And it also depends on the wavelength of interest that we're looking at. So if we look at the blue curve here, that blue curve shows the variation of penetration depth, which is defined by dp in the equation that you're looking at there, as a function of wave number. And what you'll notice is that the penetration depth is not constant as a function of wave number. It varies. And as we go to higher wave numbers, the penetration depth decreases, and it increases as you go to lower wave numbers. And what that means is that if you've got two peaks that would be of absolutely the same intensity if we're doing a transmission measurement, and one of those peaks was at 4,000 wave numbers and the other one was at 500 wave numbers, the one at 4,000 wave numbers would appear much smaller than the one at 500 wave numbers in ATR. So that's something to consider when we compare spectra that we collect in attenuated total reflection to spectra that we collect in other geometries like transmission, for example. So that's the first thing that I would like to mention about how penetration depth changes and how we can tune that with attenuated total reflection. And another thing that I'd like to mention is that evanescent wave that I discussed in the last slide, the intensity of that field is not constant throughout the depth. So for example, if we say that we've got an evanescent wave that's going about 1 micron into your sample, the intensity of that electromagnetic field is going to be much stronger close to the interface of the sample and the ATR crystal than it is further into your sample. And because of that, when we describe the depth of penetration, we're actually talking about depth of penetration where we're getting a significant amount of the infrared signal propagating into your sample. So in this case, the infrared light is propagating about 3.6 microns into your sample, and we've got 1 over E in terms of the electric field intensity. And that is what's going to define our penetration depth or information depth in this case. So now I'm going to give you a couple of examples of how altering the crystal, in other words, the refractive index of the crystal, would affect the penetration depth, and how we can depth profile by doing that, and also how we can depth profile by changing the angle of incidence. And then I'll also, at the end of this, also discuss how we can use polarization to change the penetration depth. One thing that can change the penetration depth that we have in our sample is the intensity of the electric field. And the intensity of the electric field can actually be altered by changing the polarization that we're using. And for that reason, we can actually tune the penetration depth that we have for a specific sample by changing the polarization that we use. So in this case, we're looking at a polymer again, and at this polymer, we're looking at a peak at around 1600 wave numbers. And you'll notice that we'll get different penetration depths depending on whether we're using S-polarized light or P-polarized light, and indeed even when we're using unpolarized light. So for example, if we're looking at a polymer at 1600 wave numbers with S-polarized light and a zinc selenide crystal, we're going to get a penetration depth of about 4 microns into the sample. And if we're looking at that same sample with P-polarized light with zinc selenide, would probe a little bit deeper into the sample and be looking at about 6 microns into the sample. And with germanium, if we look at that same sample with S-polarized light, we're about 400 nanometers into the sample, and we're about 800 nanometers into the sample with P-polarized light. What this means is that if we want to look at 400 nanometers at the surface of the sample, we could use germanium under S polarization, and then if we wanted to look deeper into the sample, we would switch to zinc selenide and use P-polarized light, and then we could actually look at both surface and bulk plus surface by changing the polarization and the crystal refractive index to get the maximum contrast in penetration depth. And we can also change the penetration depth by changing the refractive index of the crystal. So the table that you're looking at there shows the various crystals that are sometimes used or most commonly used for attenuated total reflection. So we've got materials such as diamond, silicon, germanium, which are probably the most widely used. And then we've also got zinc selenide, zinc sulfide, KRS5, and AmTIR. And all of these have got different refractive indices. And based on the equation that I described earlier, we can actually calculate what the penetration depth would be for a model sample. In this case, the polymer, which has got a nominal refractive index of 1.5 and at a specific incident angle, and see what that penetration depth would be. And what you'll notice here is that the penetration depth when you've got a material like diamond, which has a refractive index of 2.4, is about 2 microns into your sample. And if we change the crystal refractive index to 4.0, in other words, change the crystal to germanium, the penetration depth now drops to about 660 nanometers. So if we collect a sample at exactly the same sample and look at it with both diamond and germanium, we're going to be probing different depths into the sample. What you're looking at here is an example where we're looking at the carbonyl vibration, C double bond O vibration, when we look at a polymer sample. And in that box, that is that blue box in the spectrum, you'll notice that when we use germanium and are looking at the surface, there are a couple of peaks that are not apparent. But then when we switch to zinc selenide, we start to see those peaks. And that's because we're looking at a composition of a material where we've got, it could be a plasticizer, it could be an adhesive promoter, it could be any sort of material that's going through your sample that we're looking at and trying to track its concentration. And in this case, we're seeing more of that substance in the bulk of the sample than it is at the surface. So we don't see the peak at the surface with germanium, but we do see the peak in the bulk when you use both zinc selenide and germanium. The final example that I'm going to show is how we can change the penetration depth by using incident angle resolved attenuated total reflection. In this example, we're looking at a peak at around 1500 wave numbers that is caused by a surface contaminant on this particular polymer sample. And what you'll notice is that that peak is very prominent at 70 degrees incident angle if we're using a germanium ATR crystal, where our penetration depth is somewhere in the order of about 130 nanometers. And as we decrease the incident angle, we start to probe deeper into the sample, and that peak starts to go down until eventually that peak disappears at about 40 degrees incident angle, where we're probing about 500 nanometers into the sample. And at 30 degrees, we're probing about a micron into the sample. We no longer see that peak at all. So this is a classic example of how you could use attenuated total reflection and angle resolved attenuated total reflection to probe the surface of your sample and look for surface contamination. Thank you for listening. If you have any questions about using attenuated total reflection or any other geometry of infrared spectroscopy, feel free to reach out to the Materials Characterization Lab.